Audible, ma'am?
Ha, sir. Audible, sir. So, dear participant, today Shishendu sir will be taking hands-on session. Yesterday he has taken, so that session he will continue today. Uh, Please take over, sir.
If you are told 1 week back, no, I would have told how.
Shishendu sir, you can share the screen, sir.
Yes, ma'am. So good evening, all. Today, again, I'm starting another session. So in this session, I'm planning to discuss about a small module that is very much used in machine learning, and we'll gradually try to implement that module on the FPGA using Verilog. Because yesterday also we have seen that how to implement anything, any system or any algorithm on FPGA using Verilog, and we have seen some of the very important modules that how to uh, write a Verilog code for that. So, what are the Verilog codes we need? First of all, we require one code for error subtractor. We need one code for multiplier, and then we require one counter. Then we need dual port RAM, ROM, also register. So today I'll give you one idea that how to connect all these blocks so that we can finally design one uh, subblock for our machine learning application. So as I told you, the machine learning applications, the block I decided that is called exponential block. And exponential function has many use in machine learning application, whether it is uh, neural networks, whether it is regression algorithms, we need this exponential block. So today we will try to learn basic of this block, and gradually we try to implement this block on the FPGA. So whole implementation may not be completed today, but again tomorrow we will again try to complete this module. So I'll share my screen. So is my screen visible? Anyone can tell? Is it visible?
Yes, sir.
Yes. So you have seen many sessions on system generator in with Intel. One session on Intel FPGA also you have listened. We have seen that how to implement any system using Intel FPGA. So basically, I prefer doing this systems using Verilog from scratch. So generally, the idea is instead of if anybody wants to develop their own IP, so how to develop, that is my topic. So that we'll try to know. Generally, in either it is Intel or it is Vivado, we can see many kinds of IPs available. Here you can see one IP catalog and IP integrator also there. Using IP integrator, you can integrate many kinds of IPs available in your design. So basically, we want to we focus on how to generate this kind of IP using Vivado. So previously we discussed one error subtractor module that is very useful in any design. So we have used one parameter n here. Then we have used one multiplier. It is also very important. Then we will use the register module. So before going to other blocks, what do I do? I'll start with the basic introduction of the today's topic, that is exponential function. So already we have seen what is the use of exponential function. So application of exponential function is that basically I have written here the application of exponential function only in terms of activation functions. But you will see in the spiking neural network or in some other network also, it is used for tracking the time. Okay, so it is shown for only the activation functions. So here we have three activation functions where exponential functions are used. First is sigmoid function, then is hypertangent function or tanh function. Then we have softmax function. Sigmoid function may be used in the last layer of convolution neural network, or generally we use in logistic regression. Hyperbolic tangent function generally used in hidden layer of convolution neural network. Softmax function also it is used in uh, generally the last stage of the CNN that already we have seen in some sessions that I am not going to discuss detail, but I am saying that exponential function is used in this activation function. How? Here, this is the sigmoid function. The graphical representation is showing here. And the equation is, it is that 1 by 1 plus e to the power minus x. So we have to compute e to the power minus x. Then only we can find the sigmoid function. So sigmoid function, if you want to compute, we have to compute the exponential of x. And what is the range of exponential? What the range of sigmoid function? Range is 0 to 1. Then we can use some threshold here to select the area. That means select the class. That is, it may be zero point 0.5 for some classes, some applications. It can be more than zero point 0.5 or can be less than zero point 0.5 also possible. So this is sigmoid function. Details I'm not discussing. Now this is called the hyperbolic tangent function. So graphical representation is given here. What is the range of this function? Range is -1 to 1. So what is the equation? Equation is that it is generally equation. The main equation for exponential is that 1 minus e to the power minus x divided by 1 plus e to the power minus x. And if you multiply both sides by e to the power minus x, we'll get this equation. So this is the equation we got in terms of sigmoid. So we can represent it as like that. Tan hx, that is the tan h function, is equal to 2 into sigmoid of 2x minus 1. Okay. So I hope there will be no problem understanding what is the basic equation of tan h. So tan h is equal to 1 minus e to the power minus x divided by 1 plus e to the power minus x. And after modifying that, this equation came. That is tan h function in terms of sigmoid function. So range of this function is that -1 to 1. Lastly, we have softmax activation function. Here also you can see that exponential function is involved. So in the denominator, it is that exponential of a logit divided by summation of the exponential. So we can see here also the exponential function is involved. So we have to compute the exponential function uh, in every kind of activation function. If we can compute the exponential function efficiently, we can easily compute this activation functions. So now I will move on to the exponential function only because this application already discussed in other sessions. I will not repeat this. So moving to the exponential function. So there are many techniques or algorithms used in literature for computation of exponential function. Like you can say polynomial approximation, power series approximation, linear interpolation, Taylor series expansion, template scaling, or Chordic algorithm. So in literature, uh, authors have used this kind of algorithms to compute the exponential efficiently. So here in our discussion today, we'll try to discuss the Taylor series expansion technique for computation of exponential because this technique is very much popular and gives very uh, I can say low complexity architecture for exponential and also an approximation of exponential is given by this technique compared to the other technique like Chordic algorithm has longer latency. So I'll discuss only the Taylor series expansion method for computation of exponential. So uh, now what is important here in this all the techniques that the range of exponential, which is very, very important, the range of exponential, it's actually 0 to 1. That means you cannot compute the exponential of any arbitrary value greater than 1 or less than 1, less than 0, sorry. So you cannot compute the exponential for 5, 6, like that in hardware because the range of input to the exponential block should be 0 to 1. Maybe in some algorithm it is 1 to 1.24 up to some range, but generally it is preferred that input should be within the range of 0 to 1. Why it is? This is based upon the algorithms. The reason I am not discussing, but you should know that input to the exponential block should be 0 to 1. Otherwise, the exponential block cannot compute the exponential of any value. So the range is 0 to 1. Now, how to extend the range of this exponential block? Because I want to find the exponential of say 5, 2.5 like that. For that, there are some technique that is followed in hardware. That is that you can express the input data x as x is equal to p into log 2 base e plus q. So you have to express the input data in this format. If you can express this data in terms of this format, so at the output you will get exponential of x is equal to 2 to the power p plus e to the power q. So we will get e to the power q and we have to simply multiply by e to the power p. So we are not finding here the e to the power x. Instead, after representing that way, we are finding the exponential of q. Q here is less than 1. Q is not greater than 1. Q is in the range of 0 to 1 and we are finding the exponential of q. And finally, at the output of the block, we are multiplying e to the power q by 2 to the power p. And multiplying by 2 to the power p is very, very easy because multiplication by power of 2 means we have to left shift the data. So easily you can multiply a value with the 2 to the power p. This is the uh, technique to extend the range of a exponential. But there is one more question. Uh, does this extension of exponential worth it or not? Because the problem that is in the hardware, we find that expressing any value x in terms of this equation 5 in this format, expressing is very, very difficult. So, what is the first technique we can find to express any data within this way? Is that we have to divide the x by log 2 or repeated subtraction. So, either we have to use a divider or we have to wait for subtraction, subtraction, subtraction. So, it is very time taking as well as it's a very hardware expensive. That's why extension of exponential range is not at all advisable. That's why we avoid the extension of exponential function. Better in your application, in your algorithm, in your uh, CNN or SNN application, we have to limit the input value to 0 to 1. This is the point we have to keep in mind. So we are not doing this. We are just I have just explained this theory. Next, the Taylor series expansion of the exponential. So exponential function for positive values of x can be written in this form. So e to the power x is equal to 1 plus x plus x squared by factorial 2, x cubed by factorial 3 plus. We may have so many other terms, but I think these four terms of Taylor series can give you an approximation of exponential. So range, again, I told you, range is 0 to 1. Uh, if the value of x is negative, then we'll give this formula, equation 2, 1 minus x, x squared by factorial 2, s cubed by factorial 3. What is factorial 3? Factorial 3 means 3 into 2 into 1. Factorial 2 is 2 into 1. So, exponential function can be closely approximated by Taylor series. It will give you very close result, but not the accurate result. Now, if you want to increase the accuracy, you have to add more terms of the Taylor series. Now, it will increase the accuracy, but it will also increase the hardware complexity. So, this is why I have kept it to four terms. So, with this equation, we are starting the exponential block implementation. Next is the Taylor series expansion of exponential can be expressed this way by the series configuration. So here e to the power x is equal to 1 plus x into 1 plus x by 2 into 1 plus x by 3. This is equation 4. And for negative exponential function, we can express it like that. E to the power minus x is equal to 1 minus x into 1 minus x by 2 into 1 minus x by 3. So it is like a serial computation. First, we have to compute 1 plus x by 3, then multiplied by x by 2, then addition 1, then again multiply by x, then again add 1, and we'll get the final value of e to the power x. And if you see here, the computation of exponential function for positive value of x and negative value of x, the difference is that some sign value here uh, changing. So initially we have to add, and for negative exponent we have to subtract. The sign changes there in the equation of 3 and 4. So why both the equations are important? Because if we are computing, suppose sigmoid function, we need to compute both for positive value or negative value in the exponential. So exponential value will be computed for both positive or negative value. So both the equation we will require to make a general exponential block, because only one equation will not help you to compute any of the activation function, because input to the activation function can be either zero, either negative or positive. In this case, we need both positive and negative equation, that is equation 3 and equation 4. Okay. So the hardware will be such that it can generate the exponential for either positive or negative, whatever may be the input. So next is what is the architecture. So this is a rough architecture I have drawn here. I have not simulated the entire hardware. Morning only I have drawn this architecture. So it's a rough estimate. If any variation will be there, we will add instantly in our architecture. So what is here, if you see, first x is going to module x by 3, x by 2, and directly also. First, x by 3 will be computed, then added by 1. Then it will go to a multiplier here multiplied by x by 2. Again, 1 is added, again multiplied by x. Again, finally multiplied by added by 1. And similarly, we'll get exponential of x. So module wise, if you see, first module is x by 3. That is, x will be divided by 3. This is a module. Second module we have x by 2. That is, x will be divided by 2. And if you see here, the blocks are registered. The register blocks are pipeline register, as we have discussed in the last talk. That is, register are the pipeline registers. This is called the D flip-flop, you could say, for 1 bit. And we have discussed the Verilog code also in the last session. And delay, nothing but delaying the x by 2 signal by number of clock cycles. Here, how many delay will be there? It is not mentioned because we'll see in our architecture that how many delay will be required in our next talk. That we'll see that how many delay it will be required. And here also, X also should be delayed by number of clock cycles. So this is the architecture for positive X. A very simple architecture, and that's why this Taylor series expansion is very popular. Here we need how many multiplier? We need here two multiplier and three adder, and a few registers are required. So now one by one we will see what is the major feature of this architecture. So one important thing is that x by 3 block, that is x by 3 block is called constant multiplier. I mean this x by 3 is achieved by a constant multiplication block. This block we are going to discuss. And x by 2, again, x by 2 means it's x divided by power of 2. So x divided by power of 2 means this x by 2 can be achieved by simply right shifting the data. Okay, so we don't need a hardware or resources here to achieve this x by 2. So we have to only worry about this x by 3 here. Okay, we, we are only worried about this x by 3 block here. Other uh, and multiplier adder we already explained. So now, so x by 3 we can achieve by a constant multiplier. So we will discuss about the what is constant multiplier. So this is the block which is one of the most important combination blocks that is used to multiply any data by constant numbers. So to multiply any variable with a constant data, we generally use constant multiplier because a constant multiplier is generally have mm, less complexity compared to regular multiplier. So we will use a shift add method to achieve this kind of multiplication. So this block is also called a scale block. So uh, one example here given here, suppose we want to divide the data by 3. So divide the number is 3 is equal to multiplying the same number by 1 by 3. That is 0.33333. So this number, if we multiply with x, the same thing at x divided by 3. Now, if we convert this to binary in terms of 10 bits or 9 bits, so we can write at 2 to the power minus 2, that 2 to the power minus 4, 2 to the power minus 6, 2 to the power minus 8. In the representation, one term is missing, that's 2 to the power minus 10, because I am using here 2 to the power, I'm using here 10 bits. This equation is for 9-bit precision. But in the next line, I have written that binary of 0.333 is equal to 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. That is using precision of 10 bits. So we will have another term here, that is 2 to the power minus 10. So we have 2 to the power minus 2, minus 4, minus 6, minus 2, and minus 10. So we have power of 2, that is 2, 4, 6, and 8 and 10. So we have to shift the input data by 2, 4, 6, and 8. Because earlier I have used for 9 bits, so I have written here that 1 by 3 is equal to 20 minus 2, 4, 6, and 8. Now, okay, so here what is shown here, so first that you have to shift the input x by 2 bits, then right shift by 4 bits, 6 bits, and 8 bits, and together you can add them to achieve the result. Here it is shown another important topic called word shifting. So multiplication or division by power of 2 can be easily done by word shifting. Word shifting does not require any kind of hardware. It requires shifting logic from one point to another point words. So basically, if you see the division by 2 for sign data is just right shifting and the uh, correctly augmenting the MSB sign. That means keeping the sign, you can shift the other bits. If you see MSB here is A3, A3 going to B3, and A3 shifting to B2, A2 is B1, A1 to B0, A0 to remainder. So we need 4 bits, that's why A0 will become remainder. So this is the right shifting, left shifting is this. So multiplication and division, we don't need any hardware. It is simply achieved by what I can say concatenation in terms of Verilog. Okay. So now we have to make some blocks like right shifting by 2, right shifting by 4, right shifting by 6, and right shifting by 8. Now, because I have prepared this block for 9-bit precision, that's why I kept here RSH 8. But if you are using 10-bit precision, you have to keep RSH another block RSH 10. The RSH 2 block will shift the data by 2 bits. RSH 4 block will shift the data by 4 bits. RSH 6 block will right shift the data by 6 bits. And finally, RSH 8 block will shift the data by 8 bits. So this is the input signal going to all the blocks. The output of this blocks will be added by adder, and finally another adder. So we'll get the final result A by 3. This is a constant multiplier or scale block we are using here to achieve x by 3. So this block, entire scale block, is actually, we can say, mm, uh, consumes less hardware compared to any multiplier. Okay, that's why we're using this constant multiplier block. Is it okay? Now, we have discussed this x by 3 block, adder, you know, register, you know, multiplier, you know, register, you know, everything you know. Delay block, we don't know that how many delay it will be required here. And x by 2, we already know that it's division by 2, so we don't have to do anything here. So finally, we have discussed. Now going to the uh, common architecture for exponential, because we have seen that we have to design a block that will capable of computing the exponential for negative as well as positive value of x. For negative value of x, if you see here in the equation 4, all positive signs are replaced by negative signs. We have to subtract. So I have added one control signal called CTRL. This control signal is going to these adders that the CTRL, whenever it is 1 or 0, it will, what it will do? It will just make the changes in the adder subtractor, and it will perform subtraction or addition based on the value of the control signal. So this way, at the output, we'll get e to the power minus x or e to the power plus x. Although here e to the power plus x is written, it should be e to the power minus x or to the power plus x. And here x is the input. So it's a common architecture for exponential. And just doing the basic architecture modification you can do at your end. So gradually we'll move to implement this entire thing on the Vivado, and we will try to make it as a intellectual property in the Vivado so that others can also use. Okay. So till now, if anyone have any idea, any doubt, they may ask, because we're going to move forward. So I request the participants to ask for any kind of doubts till now.
Hello, am I audible, sir?
Yes, yes, yes.
Uh, does for like we need in positive and negative for Taylor series exponential, no sir. We have positive and negative, no sir.
Yes, yes. Hmm.
Does we require a positive negative in linear and Gaussian RBF also, sir, for machine learning?
Linear or
Gaussian RBF kernel.
see everywhere you require both positive and negative, because your input signal, it may be positive or negative. That time you have to compute both the function, minus x also, plus x also. Okay,
Okay.
anywhere.
Okay, sir.
Yeah, no. Hmm.
Yes.
Any other doubt? You can ask any doubt, because we'll move to the uh, Verilog section gradually. So if you have any doubt, so from yesterday's session, we're continuing the same thing so that we can finally build one block. Yesterday, I discussed about multiplier, adder, also register. Three blocks completed, correct? Now, we will try to do the other blocks as well. Clear? Okay. If no doubt is there, what I will do, I will go back to Vivado section. There I show one by one the blocks, and uh, maybe tomorrow we'll finally try to complete the block. Okay. So here, one more block that I could discuss in a, other blocks compared to other blocks, that is called, is it visible? Is it visible, or I have to zoom?
Yes, sir.
Okay. So this block is very, very important. If I'm just trying to make it, okay. So this block is very, very important. It's called RSH WAT. RSH WAT shift block, which I have developed. You can develop on your own, something you can develop. So here, what is this block performing? It is actually, it's a block. Input is A, output is B, and RM is the remainder. Okay? Input is A, output is B, RM is the remainder. We have two parameters. One is called N, the data width. P is the number of bits we want to shift in the right side. Okay. So P is the number of bits that we want to shift. That can be anything. So input A, output B, remainder is RM. So here, what we have done, we have just written some code here. Assign RM. How many bits we want to put in the RM? That is P minus 120. That means if suppose if uh, P is 2, I want to achieve shifting by 2. So actually, how many bits we want to shift? How many bits will be in the remainder? 2 bits. That's why it is P minus 120 means 120. That means 2 bits we will have remainder. 2 bits will be go out. Clear? That's why it is called remainder. 2 bits will be go out. Now, uh, assign B n minus 1 P minus 120. That means if you say here n minus 1 means 18 minus 1 minus P minus 1. That is equal to, you can say, so 14. Okay? 14 in the 14 bits, we are actually putting the value of A n minus 2 into is to P. Okay? Our rest bits we are filling with the C. Here C we have to uh, find out from here. We have used one always loop, and with this always loop, what we are doing that a n minus 1, that is MSB, a n minus 1 MSB we are putting in this CII. So this for loop will run from 0 to uh, 2. That means initially it will come 0, then 1, then 2. Okay. So we are shifting it here. So initially it will be C0, C1, C2, like that. And all this C value, they are putting the MSB. So simply nothing but it is like that in position A, in position of B17, B16, and B15, we are putting the MSB. Because as per the diagram, if you see, remember here, this is a diagram for right shifting. MSB we are putting at B3, B2. Okay, this is very important that MSB we have to keep in mind while the shifting, right shifting. Otherwise, we will not achieve the accurate arithmetic logic shift for the sign number. So here for 1 bit, we are putting MSB to 2 bits. Now here this is for 2 bits. We have to put MSB to 3 bits. That is 17, 16, and 15. Okay. So this is the block I have designed. You can make a better block also. But what is the advantage of this block is that I can just change the value of P here, and it will become a uh, general shift block. Okay, this block we will use for shifting any data by any bits. Okay, so and okay, let me show you the simulation of this. Why it is this block is important now. How it is working actually, I'll show you simulation. Simulation also I have done here. See now in binary I'm showing now. You must be thinking that why I prepared this kind of block while we have a ready-made command in Verilog, right? Left shift, right shift. So the reason is I need to shift the MSB also. Okay. So you see the first value here, all MSB is 1. So this is negative number. This is negative number. So minus 512, this is negative number. So after shifting, we also get the negative number only. After shifting, I got here the negative number only. So, so 512 divided by 2 will get minus 128. Clear? So this is the block for signed shifting. Now, okay, we'll move to the next block. Another block that is very, very important, I generally use for my applications, my system designs, called general delay flip-flop. So here, if you see in the diagram, two blocks I have mentioned here, delay, but I don't know how much delay I need to give here. So what I have done, I prepared one general delay block so that any number I specify in that block, it will just delay the number by specified number. Okay. So here, if you see, I have used the command here generate and a variable called genvar. Okay. So this is very simple actually. I run a for loop and call the region block multiple times. Region block also I have declared here. If you remember, this is the region block we have discussed in the last session. That region means it will delay any data by one clock period. If parameter n is 1, it will simply a d flip-flop. Region block I have used here. This region block I have called here multiple times. So initial I have taken a 2D wire here. So each wire width of n bit and varying to d to 0. So total d plus 1 number of temp register there. That is d plus 1. So here initially the temp 0. The temp 0. So which side is input? This side is the input and this side is the output. If p equal to 1. Okay. If if p equals to 1, then temp temp 0 is the input. Temp 0 is actually defined A. Okay. So what is output? Output is temp 1. Okay. Now if P equals to 2, input will be 1, output will be 2. So this way the block is actually prepared. Okay. Second line, if P equal to first line, if P equal to 1, temp 0 A, output is temp 1. Uh, if P equal to 2, temp 1. Temp 1 is basically the output of the previous block. So this way it is connected serially. Uh, I should say here, temp input is input. This is actually your input is temp 0 A, output is temp 1. And the second case, when P equal to 2, input is temp 1, input is temp 1, and output is 0. And here input is, so this way your delay block is prepared. And I can show also the, okay, I should show here. So this is the general delay block. This general delay block, if I do synthesis, so see here, all the blocks are connected here serially. If I do synthesis, it will be clear, and I show you the RTL schematic also. Sometimes while doing the uh, general kind of block, we need to observe the RTL schematic whether it is correctly connected or not. So it will be clear from the RTL schematic. So if any problem is there, the synthesis state will show that in this place we have error like that. So it is completed. I will not do run implementation. I will open the synthesis design, and then we will go for the we'll go for the, okay, we'll go for the, synthesis. So here, okay, I should show here. So this is the general delay block. This general delay block, if I do synthesis, RTL schematic. If you see here, so schematic, if you see, this is the first block, this is second block, fourth block. So total four block we have because in the main design, if you see here, we have given the initial parameter 4. We need to achieve 4 delay only. So 4 delay means 4 register will be connected in serially. So here also if you see 4 blocks are connected serially. So what is the input here? Input is here A. After that, what is the next input is so this is the next input, next wire, and this way it is generally connected. Okay. So this kind of blocks are very helpful in preparing the general blocks. So once the general block is prepared, we can easily make it as a IP. Okay. So this kind of technique I generally follow if we have to make a simple IP. So I think we have discussed all the major blocks. General delay block we have discussed the ISH wired block. So gradually we'll start the exponential block. So can I ask for doubts? Anyone have any doubt? Because now we are going to start the next topic, that is the compilation of all these blocks. Today we're not going to start because we don't have that much time. Next day we'll prepare, start from the beginning, and we'll one by one connect the blocks, try to achieve one architecture, and then what we will do, we'll give input vectors and try to simulate it, and we'll try to implement it. We'll try to find the performances area, what are the main things we have to observe in a PG implementation. Then we will find the maximum frequency. We will try to find the other parameters as well. It's a complete process of this exponential block we try to achieve, and finally we try to make it as a IP, and then also, and then we can also try to use this IP in our design also. We will see, and if we have time, we also see that how to use this exponential block in kind of in terms of in the application of activation functions, and how to uh, uh, design the architecture for finally the activation functions. That also we'll see. So if any doubt is there, please, any doubts or questions, please ask. Any doubt? Okay. Zoom it, sir. So it was not visible here. Zoom, how to zoom? Okay. Basically, I think there was some font size options. I forgot what it is. Okay, apart from that, any other question? Am I audible?
Yes, sir.
Okay, so the thing is that Cordic, do we have IP for Cordic also? Yes, IP for Cordic is available. I can use. It is available in Vivado also. It is available in the Intel also, and if we can use the codic here also. The codic basically how it computes the exponential. In exponential, the codic block first computes the sine hyperbolic, then computes the cos hyperbolic. Okay, so sine and cosine computed by same codic, and together they add it and subtract it, and they will get the exponential of x. Here, apart from that, any other doubt? Signed and unsigned bits are both calculated. What does it mean? Because signed and unsigned, we need to consider here. Uh, for multiplier, if input is signed, that means input can be negative or positive. So every block should be signed. Okay, and for uh, codic also computes the same way, signed. Generally, it's signed only we do in codic. If any other questions have,
Uh, Sir, am I audible?
yes, audible.
Uh, can we integrate Cordic with Tyler series, sir?
Why required? You can use either codic or telesis.
For
What purpose you want to use codic?
like uh, impl- uh, one of the base paper I have been working on, they have
Mhm.
implemented like a Cordic and also including the Tyler series approximation.
Now, the first question is if we can do approximate the exponential function using Taylor series, then why to do using this codic? Because it will be redundant, no?
Yes. The Tyler series has been the efficient one than the Cordic one, sir. Is
Yes,
that
yes, obviously. Obviously, codic actually, codic depends on the width of the data. That means if the data width is 18-bit, it will give some moderate result. If we increase the data width 24, it gives more good result. And also, the latency of codec block depends on the data width. If we increase data width, that means latency of codec will be increased. So there are a lot of issues in codec. It's not that easy. So if you require very low latency hardware, then offer this Taylor series. Okay. Yes. Achha, ma'am.
thank
Sir, I have one question. Like I was working on one base paper of Codic and
Hmm.
reducing the computations of FIR filter using Codic in the twiddle factor. So is it so it will give a optimum result, or I should search for some other computational thing apart from Codic, because there
Your
are
question is
many
that in FIR filter, codec,
F50 F50.
FFT. Okay, that is a
Yes.
question. Actually, good question.
So sir,
See, codec actually is very much good for this. I can say FFT because codec is very good for rotation, and there are many papers on FFT. They perform the FFT using codec. Okay, but again, the question is the of the accuracy of the codec is not that good. If you see,
Yes, sir. I
so
have implemented it, and I'm facing the issue with accuracy only.
yes,
So how to improve the accuracy so that results can be good?
to increase the accuracy of codec, we need to increase the data weight. If you increase data weight, your accuracy will be good. Again, the question is, if you increase the data weight, the latency also will increase in codec. Am I right? So
Yes, sir.
uh, You can check with the other kind of FFT, like if I say directly the mm, parallel implementation of Radix 2 architecture that is available is uh, on
Okay.
the okay.
Okay, sir. Okay.
Or
Thank you
you
so
can
much, sir.
say many architectures are available on the internet for FFT without coding also. Okay.
Okay. Okay, sir. Thank you.
Any other doubt? So next day, we want to implement this entire thing, entire this exponential thing on the FPGA. I'll show you everything on the Vivado. So any other issues that you want us to discuss, like many you are facing how to, they are telling that how to insert data or something like any particular issues we have to address. Anyone can ask that so that we can plan.
Sir, I have one small query, but it's not with that a related workshop. Actually, I have installed my Vivado on Linux, and I have always worked with the Windows. So I have an issue how to evoke Vivado from that. That is one question that is in my mind. I'm not getting correct answer. So this is I would like to ask if anybody knows how
Okay,
to
okay.
evoke Vivado from Linux. So it will be a great help if anybody knows the answer.
Okay, you put that question in the chat box. We'll see if you can solve it or not.
Okay, sir. Thank you so much.
Okay, okay, okay. Thank you, all of you. Tomorrow again we'll meet.
Participants, any doubt? Anybody is having any other questions? Okay, I guess no questions, sir. So thank you, Shishendu sir, for such a wonderful hands-on session. So we'll join for day 3 sessions from tomorrow. Thank you all for joining the FDP for today. So please feedback form is shared for today's sessions. Please share it all. Okay. Thank you all.